Our next speaker is Dima Kharzeev, who will continue with his talks on chiral matter. And I apologize for the delay. Go ahead, Dima.
Okay, hello everyone. So last time we talked about chirality in classical physics and in particular fluid dynamics. So today we will continue with chirality in gauge theories and in quantum field theory in general. So let me start from the simplest gauge theory that we all know and love, Maxwell electromagnetism. And in Maxwell electromagnetism, as you can see explicitly, there is no asymmetry between left and right. Nevertheless, it is possible to introduce this asymmetry in gauge theories. And geometrically, gauge theories, gauge fields represent an example of so-called fiber bundle. So you have some space time, and then a gauge transformation at each point in space-time brings you along a line. And locally, this map is just defines a product space. But globally, as you can see in this example of the Möbius strip, the bundle can be topologically non-trivial. And of course, in this particular case, you can get asymmetry between left and right. And so now we understand that to classify topology of gauge fields, we really need to develop some topological invariant of this fiber bundle space. So this problem was solved quite some time ago by Soeren and Simons. So in section, in particular, in section 6 of their paper, they consider 3 manifolds, and they classify the topology of these manifolds in terms of Riemannian connection theta and a curvature tensor omega. So here is their answer. And now we would like to figure out what does this answer mean for physicists. So luckily, the dictionary of geometry is easy to translate into the language of physics, because Riemannian connection in our language is just the gauge field, and the curvature tensor is just the field strength tensor. So if we take the answer by Soeren and Simons for 3 manifold, then this answer for us can define the following quantity. And if you look at the first term in this expression, then you see that epsilon ijk fjk is just a magnetic field bi. So what we have here is the scalar product of ai bi, or a dot b, integrated over space. And in fact, this integral of a dot b over space has been known to people doing magnetohydrodynamics for a very long time under the name of magnetic helicity. So what is the physical meaning of magnetic helicity? You know that the lines of magnetic flux have always have to be closed because we don't have magnetic monopoles. And therefore, the lines of magnetic flux can form, let's say, some circles, which are topologically trivial configurations, but they can also form topologically non-trivial knots. So we have already encountered a knot when we talk about DNA molecules. So here is the simplest right-handed trefoil knot of magnetic flux. And if you evaluate the integral of A dot B for this configuration, you will find that it's +1. Now, if it were a left-handed trefoil knot of magnetic flux, it would be -1. And if it were just a circle, it would be 0. So it would be a topologically trivial unknot. And of course, we can also form more complicated chiral knots, but the value of magnetic helicity would always be integer. So now the second term here is a little harder to visualize. It appears only in nanobillion gauge theory, but again, it also classifies the chirality of the nanobillion gauge field configuration. So now this answer has been given for 3 manifold for 3 spatial dimensions. And now when we talk about physical systems, we like to think in 3+1 dimensions. And so the question is, what is the meaning of Chern-Simons invariance in 3+1 dimensions? So do they lose any meaning? Well, the answer is no, they don't lose a meaning. However, in 3+1 dimensional space, they are no longer conserved quantities. And you can have transitions between sectors with characterized by different Chern-Simons invariants. So again, in the example of magnetic helicity, this transition is quite easy to imagine. So this transition would just correspond to a magnetic reconnection of magnetic flux that would turn, let's say, this right-handed trefoil knot either into unknot of 0 chirality, or in a state with chirality +2, so a more complicated configuration. So these magnetic reconnections are really abelian analogs of instanton transitions in non-abelian gauge theory. So now to develop more intuition about Chern-Simons forms, we can also consider circularly polarized light. And so intuitively, it's clear that circularly polarized light, comes in left-handed and right-handed forms. So it certainly possesses chirality. And we can think of using magnetic helicity to characterize helicity of this circularly polarized light. However, there is one problem with this, because magnetic helicity itself does not obey electric magnetic symmetry or electric magnetic duality of Maxwell equations in vacuum. That was, of course, pointed out in 19th century by Heaviside and Larmor. So it is possible to enforce this electric magnetic duality by introducing, in addition to the usual gauge potential A, also the dual pseudo vector gauge potential C. So this was also proposed a very long time ago by Bateman in 1915. And then, just like in Coulomb gauge, electric field is given by minus time derivative of ordinary gauge potential. Magnetic field is given by minus time derivative of this dual gauge potential. Of course, magnetic field is a pseudo vector, and that's why this gauge potential C also has to be a pseudo vector. So in this case, the electric magnetic transformation is induced by this rotation in the space of gauge potentials. And we can define the optical helicity by adding Chern-Simons terms for A and C. So in this case, we see that Chern-Simons forms indeed describe the optical helicity of circularly polarized light. So I apologize for some background noise. My neighbors decided to cut down a big tree, so we will have to endure this. Okay, so now the optical helicity that we have constructed is invariant under electric magnetic symmetry. It is a T even and P odd quantity. It is conserved in vacuum, but if we have interactions with some chiral matter, then this optical helicity is not going to be conserved, because we will be able to transfer helicity from light to matter and vice versa. And this is, in fact, the physics of the chiral anomaly that we are going to discuss later today. So now, as I said, these transitions between different Chern-Simons sectors happen all the time in non-abelian gauge theory. So this plot from Derek Leinweber shows the density of the time derivative of A dot B, which is E dot B, so FF dual. And you can see that in the vacuum of quantum chromodynamics, these transitions happen all the time. So blue regions here are the regions which decrease chirality, and red ones are the ones which increase chirality. So you see that this chirality change in transitions happen in the vacuum all the time. But I have to warn you that even though the fact that these transitions happen all the time, I think is firmly established, the way these configurations look really depends on whether you apply so-called cooling procedure by removing some short wavelength component of gauge fields. So this is done on cooled configurations. If you don't do the cooling, then instead of this nice round blobs, you see some surfaces. But the physics is the same. These are the surfaces on which chirality gets changed in the vacuum. So now gauge fields interact with fermions. So electric and magnetic fields interact with electrons. They also interact with electric charges of quarks. And if we have non-abelian gluon fields, then they couple to the color charges of quarks. And because, as we discussed before, chirality can be transferred from gauge fields to matter and back, we also have to consider what happens to chiral fermions in the presence of these transitions. So there are several kinds of chiral fermions that we know. There are Dirac fermions described by Dirac equation. There are Weil fermions, which is the limit of Dirac theory for zero quark mass, in which case there are just two components of this spinor psi. And then there are Majorana fermions. And in this lecture, we will mostly deal with Dirac and Weil ones. So now remember we talked yesterday about the chiral transport. So we discussed Archimedes' screw. This was a chiral object which we started to rotate, and then it either transported water, or if it was a chiral propeller, it started to move in water. And so today we are going to discuss a very similar phenomenon. Suppose we have a background magnetic field, which is analog of the angular velocity. It's the same pseudo vector. Suppose I have a fermion of particular chirality, let's say left-handed fermion. It interacts with magnetic field. And then the question is whether in this situation I will be able to generate an electric current flowing along or against the direction of magnetic field. Because this is a vector and this is a pseudo vector, we know that this requires parity breaking, just like in the case of Archimedes' screw. But if I have fermions of particular chirality, let's say left-handed, then this condition is satisfied, and I might hope to get a current which would be parallel to B. So let us make this proposal a little more explicit. Suppose I have a gas of massless charged Weil fermions of a certain chirality, let's say left-handed. I put this gas in an external magnetic field B. Then the fermions sit on Landau levels. And on the lowest Landau level is not degenerate in spin. And the projection the spin is always parallel to magnetic field if the fermion is positively charged. And then I know that this is a left-handed fermion, which means that projection of spin on momentum for this fermion has to be -1. So the fermion sits on Landau level. Its spin is parallel to magnetic field. It's free to move along the direction of magnetic field. And so naively, I come to the conclusion that in this situation, I must get a current which is parallel to magnetic field. So this was a really nice pioneering idea of Alexander Vilenkin, who is a well-known cosmologist at Tufts. So he proposed this in 1980. Then, according to his recollection, he came to report this at a conference at which C.N. Young was present. By the way, today is 100-year birthday of C.N. Young, which we are going to celebrate later in the day at the Simons Center. So it's kind of a good day to discuss this. And C.N. Young got up and said that this proposal makes no sense because there could be no currents in equilibrium. And one can formulate it in terms of Bloch theorem or in other ways. And in fact, shortly after this, Alexander himself confirmed that these currents cancel out in equilibrium, and this effect does not exist. Okay, so a similar story actually happened in the condensed matter world. In 1983, Eliasberg at Landau Institute in Chernogolovka, close to Moscow, put forward idea that crystals with broken inversion symmetry in a magnetic field would be able to develop currents flowing along magnetic field. So he developed this idea together with his then students, Leonid Levitov and Yuri Nazarov. But later on, with the help of their Landau Institute colleagues, they also concluded that such currents do not exist. So nevertheless, this is not the end of the story. And there is actually a way for this effect to survive. And the way out for this effect to survive is the chiral anomaly. So what is the chiral anomaly technically? So if we have a theory of massless fermions, then you can just compute the current, which is generated by chiral transformation, rotation of the phase with gamma 5. And this axial current, the current of chirality, if you decompose it in terms of the currents, vector currents of right-handed and left-handed fermions, is the difference between the currents of right-handed and left-handed fermions. So to get a non-zero axial current, you must have right-handed and left currents flowing differently. So classically, this current is conserved, as you can just conclude using equation of motion. So you just compute explicitly this derivative, use Dirac equation for massless fermions, and conclude that this is equal to 0. Physically, this is because left and right-handed fields decouple in the massless limit. There is no coupling between right and left fermions, and therefore the corresponding current is conserved. However, this conservation law is destroyed by quantum effects. So even though it's true classically, it's not true quantum mechanically, as was pointed out by Adler and Bell and Jekyll. So the point is that once you compute the corresponding diagram, there is a loop contribution to this divergence, where this is the propagator of a charged fermion. And the corresponding divergence does not vanish. It's equal to E squared, because there are two couplings of gauge fields, times E dot B, which is a gauge invariant and a pseudoscalar combination of gauge fields. So a textbook example of chiral anomaly is decay of a neutral pion into two photons. And in fact, Adler and Bell and Jekyll were not the first to consider this decay. This was done by Jack Steinberger, who passed away recently. So of course he got his Nobel Prize for experimental discovery of muon neutrino. But even though he was a theorist, already in 1949, he used Feynman diagrams which were proposed by Feynman just 2 months before this work was submitted to evaluate the decay rate of neutral pine into 2 photons. So this is even more impressive because Steinberger actually received his training as a chemical engineer. And so for someone with training in chemical engineering to master Feynman's new method in a couple of months and to apply it, I think is really quite remarkable. And some time ago, I read his original paper and found a very interesting footnote. So Steinberger attributes the idea for the gamma instability of neutral mesons to Oppenheimer. So Oppenheimer was actually the original author of this idea. And there were also a calculation done by Finkelstein a little before Steinberger, but Steinberger really did it in a form which is quite close to the one that we are used to now. So chiral anomaly is still being studied in Primakov effects and conversion of photon into neutral pine in Coulomb field. And you can see that the available experimental studies, which continue to this day, are quite nicely consistent with the prediction of anomaly supplemented by the chiral Lagrange. So now this is a very interesting story, but what does it mean for our example of chiral fermions in a magnetic field? So the fact that axial current is not conserved, of course, means that the chiral charge is not conserved because the chiral charge density is defined as the temporal component of the axial current. And this tells us that time derivative of the chiral charge density does not vanish. So chiral charge is not conserved. And therefore, if I prepare a chirally imbalanced state of chiral fermions, the state in which the numbers of left-handed and right-handed fermions are different, this means that this chiral charge can decay. So the Fermi energies of left-handed and right-handed fermions, can become equal. And this means that a chirally imbalanced state of chiral fermions is not a true ground state of the system. So this means that C and Young's objection to Vilenkin's idea does not apply, because this objection and block theorem applies only to the true ground state, equilibrium state of the system. And anomaly tells us that a chirally imbalanced state is not a true ground state. Moreover, you can already see where I'm going, because suppose I have prepared some chirally imbalanced state characterized by this chiral chemical potential, which is the difference of chemical potential of right-handed and left-handed fermions. Then I put this in a magnetic field, and then you can see that the same triangle amplitude will now allow the decay of this chirally imbalanced state in an external magnetic field with the generation of a vector current. Okay, so it is also instructive to consider chiral anomaly in the language of condensed matter physics, because it really illustrates the essence of the phenomenon quite well. So suppose I have this single band. So, and suppose that this is the Fermi energy. You see that close to Fermi energy, I can approximate this band as being linear. And so I can think of right-handed chiral quasi-particle here and left-handed chiral quasi-particle here. And in equilibrium, of course, this is the Fermi energy. So all states below Fermi energy are occupied and above Fermi energy are empty. But now suppose I put this system in parallel electric and magnetic fields. So then in parallel electric and magnetic fields, I will have this motion of left-handed states down this band, and they will go down, and then they will go through the bottom of this band, and then they will start emerging here above the Fermi energy. So I will create a chirally imbalanced state where the chemical potential of right-handed fermions is different from the chemical potential of left-handed fermions. So I will generate a non-zero chiral chemical potential. So you see that this is not a ground state of the system, because the system can relax back to its ground state. You can also see that how the phenomenon of anomaly comes about. Because here, if you consider the spectral flow across the band, you know, nothing really disappears or appears out of nowhere. It's just the spectral flow along this single band. However, if you insist on describing this in terms of effective chiral theory, which is valid only where this band is linear, so only where the fermions can be considered as chiral, then for this effective theory, I would have to introduce an ultraviolet cutoff. So physically, I would have to place it at energy where the band starts to curve. And then in this effective chiral theory, you see that left-handed charges will disappear behind this ultraviolet cutoff, and right-handed charges will appear from behind of this ultraviolet cutoff. And that's why in this effective chiral theory, this will be viewed as an anomaly and as a consequence of ultraviolet regularization of my effective field theory. But the essence of the phenomenon of the anomaly is really the spectral flow, which is present at all energy scales in the system. And because it is present at all energy scales, chiral anomaly links phenomena in the infrared with very low excitation energy to phenomena in the ultraviolet. So that's why people say that chiral anomaly acts as a bridge between ultraviolet and infrared phenomena. So because of this, chiral anomaly, as we will see, can affect macroscopic behavior of systems with chiral fermions. Okay, so this is a slightly more technical slide, which I put here to illustrate that often people think of anomaly as a phenomenon which exists only for massless fermions. It's not true. you can explicitly work out dependence on the mass of the fermions. And as long as it's not too big, the phenomenon still persists. And for example, in a condensed matter systems, this opens the possibility of anomalous transport in narrow gap semiconductors. Okay, so now I already explained how the chiral potential in the presence of a magnetic field gives rise to the vector current. So this is really a corollary of chiral anomaly. You can compute it, the resulting current explicitly. The coefficient here actually appears to be exactly the same as Vilenkin found it, but this time the interpretation of this formula is different, and we actually find the current which does not vanish. The coefficient in this current is completely fixed by the chiral anomaly. So if you look at this as the operator relation, then there are no corrections to this formula. So it's not leading order in coupling. It's a complete expression for this chiral magnetic conductivity. You can also do this by other methods. So we gave 4 different derivations in our paper with Kenji and Harman, but the result is always the same. And we have already discussed the hand-wavy physical interpretation of what's going on. So if you have a magnetic field, and you have positive fermions, let's say up quarks, and negative fermions, then they sit on Landau levels. They still are free to move up and down. Their spins are pinned parallel to magnetic field for positive fermions and anti-parallel to magnetic field for negative fermions. But in the absence of chirality imbalance, there is obviously no current. Now, if you prepare a configuration with an excess of right-handed fermions, for example, if we have a background of an instanton, which prepares for us only right-handed quarks, then being right-handed for a positive fermion means moving in the direction parallel to its spin, and this is up. Being right-handed for negative fermions, again, means moving in the direction parallel to its spin, but its spin points in the opposite direction, and that's why positive fermions move up, negative fermions move down, and you induce an electric current in the system. And of course, we have an infinite supply of fermion and anti-fermion pairs in Dirac vacuum. So this picture has been confirmed by a number of first principle lattice computations. So I will not show all of them. So this is one of the early ones by Arata Yamamoto, who shows the current linear in U5 and the current linear in B in the direction of magnetic field. And there is also an interesting work by Braguta and collaborators, where they investigated the chiral magnetic conductivity across the chiral symmetry restoration transition. So they found that if you have a chirally broken phase, which is induced by effective coupling, then the chiral symmetry breaking takes place, And the order parameter of this chiral symmetry breaking is psi bar psi, the chiral condensate. So you can see the chiral condensate growing up across this chiral symmetry breaking transition. And if you look at the chiral magnetic conductivity, then the chiral magnetic conductivity also drops across this chiral symmetry breaking phase transition. So spontaneous breaking of chiral symmetry prevents the chiral magnetic current from propagating. So I have to add that there is some special case of pion superfluid. And in fact, it is possible to construct the chiral magnetic current in the pion superfluid case. But nevertheless, this is a very interesting and suggestive phenomenon. So similar anomalous phenomena. So this is the phenomenon that we discussed so far. Similar phenomenon can be induced by vorticity. And of course, this is not surprising because by Larmor theorem, omega times vorticity is analogous to magnetic field. There is also an axial current that you can induce in the presence of ordinary chemical potential in a magnetic field. There is an axial current that can be induced by vorticity. Here, an interesting feature of the effect is that you can induce an axial current by vorticity even at zero chemical potential, just due to temperature effects. And there is also an interesting non-universality of this vertical conductivity. There are corrections to it proportional to coupling. And recently with Matteo Bozzegli, we interpreted these corrections in terms of anomalous gravito-magnetic moment of fermions. So basically, this is the effect of equivalence principle breaking at finite temperature. So at finite temperature, Lorentz invariance is gone. Equivalence principle, which tells us that there is no anomalous gravito-magnetic moment, is also gone. And there is a possibility to induce radiative corrections to this conductivity. Okay, so now discrete symmetries were a guiding principle for us. And we already know that chiral magnetic conductivity is a parity odd effect. Mu5 is asymmetry between right-handed and left-handed fermions, so it's manifestly parity odd. But what is even more interesting is that both magnetic field and electric current are quantities which are odd under time reversal. And so this means that the chiral magnetic conductivity is even under time reversal. And this means that we are dealing with reversible non-dissipative dynamics. And this is why I emphasized so much this reversible dynamics of fluids in the Stokes regime, and in particular, the non-dissipative reversible dynamics of chiral propulsion in Stokes fluids. So this conductivity, which is even under time reversal, is highly unusual. So for example, if you look at ohmic conductivity, then electric current is odd under time reversal. Electric field is even under time reversal. And so the ohmic conductivity is odd under time reversal. And it's clear why it is an odd quantity, because it describes processes of dissipation in which entropy is produced. And once you start producing entropy, you generate an error of time, and we are talking about non-dissipative dynamics. So the physics of chiral magnetic effect is completely different. It is the physics of a non-dissipative phenomenon. And this is why I would like to discuss connection and similarities and differences between the chiral magnetic effect and the physics of superconductivity. So we all know that long before the microscopic theory of superconductivity was built by Bardeen, Cooper, Schrieffer, Bogolyubov, and others, there was a highly successful phenomenological theory by London brothers who postulated that superconductivity can be described if electric current were proportional to the gauge potential, plus, of course, the gradient of the superconducting phase. So now, if you simply postulate this relation and you use a Coulomb gauge, then you see that if you take a derivative, time derivative of this relation, you immediately find on the right-hand side electric field, on the left-hand side time derivative of current. And this relation tells you that a constant electric field gives you a current which grows linearly in time. And so if you try to define a conductivity similar to Ohm's conductivity, the resulting conductivity will diverge and the resistivity will vanish. So this, of course, is very well known. But for now, what I want you to appreciate is that if you look at London's formula and analyze it from the point of view of discrete symmetries, then you see that both J and A are vectors, and they are both odd under time reversal. And so if you view this coefficient as some kind of conductivity, then it is also a T-even conductivity. So you can tell immediately from this relation that this formula is going to lead to a non-dissipative transport. So in our case, the relation is J is proportional to mu5 times B. Mu5 is induced through chiral anomaly. Again, if I apply parallel electric and magnetic fields, the mu5 that I'm going to get from here will be E dot B times time, because this is time derivative of chiral density that sits here. And so I have J proportional to E dot B times time times B. I differentiate it with respect to time, both parts, and I find the relation that a constant electric field is going to give me electric current growing linearly in time. And so the whole analysis applies. Of course, the underlying physics is completely different. We don't have any condensate. We don't need, to restrict gauge symmetry in any way, because B is a gauge invariant quantity. This phenomenon is not killed by magnetic field as usual conductivity, but actually exists due to magnetic field. But from the point of view of discrete symmetries, the analogy, I think, is quite interesting. And in real life, let's say, if we think about real materials, the constraint comes from the fact that chirality of fermion quasi-particles is not strictly conserved. And so in real life, instead of time, you get here some chirality relaxation time. but this is still a time which is orders of magnitude larger than the typical transport time. So it makes sense to think of chiral magnetic effect as a nearly dissipative phenomenon in real materials and in QCD plasma. Okay, so 53 minutes passed, so let me stop right here and ask for your questions.
Does anybody have any questions? No?
Hi, Dima. Sorry, I had a question for you.
Go
Yeah,
ahead.
so when you show the chiral condensate plot and the chiral conductivity, is it out of equilibrium, or you're assuming that, of course, this chiral magnetic effect has a large relaxation time, so you can take it to be near equilibrium. Is it so?
Yeah, so here they actually considered a system which possessed non-zero chiral chemical potential. So the system is out of equilibrium, and that's why the current exists. But chirality relaxation time was quite long. So it's kind of a steady out of equilibrium state.
Okay, so that's why you could, this psi bar psi is just in the equilibrium theory.
Yes.
That's why you could compare it with that. Okay.
That's exactly.
Thanks a lot. Thanks for the very nice talk.
Thank you.
I think Masood Shakri has a question. Would you like to go ahead, Masood, please?
Hi, thank you. My question is about the Chern-Simons story and building a kind of magnetohydrodynamic story out of Chern-Simons theory.
Yes.
First, I mean, actually, we did a calculation like a few months ago based on this Chern-Simons story that is presented in your paper, for example. And it seems that if this theta term has a non-vanishing spatial gradient in the equilibrium, then the equilibrium of this story will not be stable.
Let me first understand the computation that you did. So you added a theta term with spatially dependent theta. Is it correct?
Yes.
Okay. So then you get terms which are proportional, for example, to, in magnetohydrodynamics, you get induced charge, which is proportional to gradient theta dot b, correct?
Yes, but we assume that the fluid is neutral, so P dot B is in equilibrium. P dot B is equal to 0, and also the charge density is equal to 0. Both of these guys are equal to 0.
Okay, so let me ask another question. Is the electric conductivity of your fluid infinite or finite?
Finite. It is finite.
Finite. So this means that you can have accumulation of charges due to gradient theta dot b.
Yes, we just we apply some perturbation to this equilibrium, and the equation, for example, we have this Ampere's law, and if you assume the Ampere's law in Fourier space, I mean, if you make a Fourier transform, the eigenmodes will be like omega is equal to minus I sigma E plus some terms. So this is a gapped, there's a gapped mode here. But the thing is that it seems that in Chern-Simons story, if you have non-vanishing a gradient for theta in equilibrium, then this sigma is effectively modified, and you cannot ensure that the sigma is is always positive. It can be effectively negative in some regions of space.
No, I think I understand why this happens, because you see, if you have a magnetic field and a gradient of theta, this means that you generate dipoles of electric charge due to gradient theta dot b. And this gradient of electric charge creates itself an electric field, which can be either parallel or anti-parallel to external electric field. And this can reverse the flow of current, so it can formally give you a negative conductivity, for example. So I think it's reasonable.
And do you think that this is a problem for what Chen-san was doing?
I don't think, no, it's not a problem at all. It's just, I just tried to explain the physics. I don't think it's a problem. I think it's physics.
Thank you. Thank you very much.
Very good. I think Mithat Unsal has a question. Mithat, would you like to go ahead, please?
Sure. Hi, Dima.
Hi, Mithat. Great to hear from you. Yes.
Thanks for your nice talk. Can you comment on, possible implication of the fractional instantons on the chiral magnetic effect and related phenomena? You can also comment on, for example, the presence of some discrete tooth flux. It is more or less same question.
Yes. That's a very good question, and I think we should just discuss and see what are the implications of fractional instantons. I don't want to make a fool of myself trying to explain you what fractional instantons are.
No. I'm sorry. I think as the chairperson, I find that a somewhat cowardly answer, but I guess I'll have to accept it. But I thought Mithat explained everything very clearly.
Yeah. Well, in the first approximation, let me make a less cowardly statement. I think in the first approximation, fractional structure of instantons is not going to matter for electric current, right? Because you have this fractionalization in color space, right? And here we are talking about abelian response. So all I want from my instanton is not a particular orientation in color space, but just a contribution to mu5. And so as long as I get the same mu5, I'm probably going to get the same current, and the fractionalization of instantons probably is not going to matter. But this is kind of just a first order approximation to the answer. Maybe I should think more about this.
Yeah, okay. So we can actually chat in private. Also, for example, in the background of tooth flux, there will be other talks about this by Tony, for example. There is also topological charge becomes quantized in units of 1/n, for example. That should have somehow some impact.
This is a different. This is a slightly different question, and this I think should matter, right? Because quantization of flux will affect the current. It will may introduce the quantization of current.
Okay. Thank you. Let me think about it.
Let's talk about this.
Sounds good.
No, but if I can comment too, without hurling insults, because the fractional instantons, you can't have a quark in the presence of a single fractional instanton, but presumably there's some natural binding or interaction between a single quark and one of these fractional instantons, although I have no idea what it is.
So, Rob, there is a refinement of the APS index theorem. So it tells you you know, given a fractional instanton, how many zero modes, Fermi zero modes it accommodates. And so in some circumstances, actually, all of the zero modes may be localized to one of the fractional instantons. But if you turn on some flavor background, for example, if you turn on some SUN flavor background, you can change this game. You can make, for example, each fractional instanton having certain number of Fermi zero modes. But this becomes a more theoretical question. I mean, not certainly relevant experimentally, but I think the crucial point I want to mention is that there's an index theorem called Nysinger index theorem, and it is sort of for Dirac operator defined on R3 cross S1 in the presence of the holonomy. So I think that will be crucial somehow in the discussion.
Yeah. Well, perhaps we should end the discussion here, though, and thank Dima for a very beautiful talk.